Okay, we're going to finish up counting from yesterday. So make sure you have your notes ready to go. We finished with permutations. So we'll review like the three types of examples that we already have done, and we'll add in the third one. So our first method of counting was the multiplication principle. And the multiplication principle told us that we can simply multiply each of the number of ways per event. So, if I toss a dice 4 times, and I want to know the number of outcomes, the number of ways I can get that to happen. Well, if I'm going to toss it 4 times, how many options are there on a 6-sided dice? Well, 6 sides, right? So 6 options, 1, 2, 3, 4, 5, and 6. So if I'm going to toss it 4 times, then I have 6 options for a roll, the first roll. This is first roll. And the next one, second roll, 6 options times 6 options for the third roll, and 6 options for the fourth roll. And of course, in this case, we aren't taking a number off the die and changing the probabilities that way. It still has 6 sides each time. So that's 6 to the 4th, and that's small enough number that we could actually put it in the calculator, and I get that 4 by adding these exponents right here. So another example of this is like if I had 4 shirts, 4 distinguishable shirts. They aren't all white shirts. So I have 4 shirts, 5 pants, and maybe 2 ties. And I want to know the number of outfits.
40.
Yes, because I'm going to do 4 times 5 times 2, which is 40. Evan, you had a question?
No, I was telling you what 6 and 4 were.
Oh, okay. So any questions on using the multiplication principle? Now, this is the simplest case. Now, usually the mistake is assuming that all the cases come down to a multiplication principle, and that's not true. They get a little bit more complicated, and we're going to use our toss of a coin. So let's do a coin toss. And we're finding the number of ways a coin toss can happen if I toss it 3 times. And this was actually in our notes from yesterday where we said, all right, we can do a tree diagram and we could branch off, and we should be writing this down, and we have heads or tails. That's our first toss. And then we have heads and tails for the second toss. So this all was toss 1. This all here is toss 2. And then we branch off again. Heads, tails, heads, tails, heads, tails. This is assuming it's a fair coin, right? It's not one of those trick coins. Toss 3. Okay, so if you had a weighted coin, you might disproportionately get more heads or tails depending upon which side was heavier. But this is a fair coin, so it's equal. And then as we look across this, we get all the possibilities. We can count these. We have 1, 2, 3, 4, 5, 6, 7, 8. And that verifies our multiplication principle. We have 2 possibilities for the first toss, 2 possibilities for the second toss, and 2 possibilities for the third toss, and we get a total of 8. But when we do a tree diagram, we get all of them. We get an actual list here. So this is our tree diagram. I could start listing out each of the outcomes by reading it. Do you see how I'm getting? Like if I read the next one off. Heads, tails, heads. And then heads, tails, tails. And then tails, heads, heads. And then tails, heads, tails. and then tails, tails, heads, and then tails, 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 all tails. Okay, so this leads us to the question, and we started to allude to this yesterday, is this event, in this event, actually different?
No.
And it depends. It depends. Justin's saying no, that they're not different. Why are you saying that they're not different?
Because in each one of them... Wait, never mind.
In each one has...
2 H's and 1 T.
Yeah, 2 heads and 1 tail. So the question becomes, does the order matter?
No.
And well, it does. It depends on the context, right? If I'm one at a time tossing the coin and saying, like, if we were like, if you lose, then you're out, and then we all did this, and then some of you would get out, right? Depending upon the order. But if I'm just tossing the coin to see the number of ways that it happens, then we might argue, well, then the order doesn't matter because I'm just, counting how many heads I get versus how many tails. So, order. That's a question that we're going to have to ask. Now, yesterday we started with permutation, or we ended with permutations. And permutations are when order matters. Okay, and we had a formula for that. So we have NPR equals n factorial over parentheses n minus r factorial. And we said that n is the number of objects that we have, number of things, and r is the number I want. So let's set up another example of this. If we had, for example, 20 students run for president, vice president, and secretary of student government.
Oh, man.
How many outcomes are there?
Wasn't he like 20 times 19 times 18? Good one.
Yep. How many outcomes are there? And what Evan was saying is correct. He said, well, there are 20 people running, and presumably they prefer to be president. We select our president. That means I have 19 left that could be vice president, which means I have 18 left that could be secretary. So that is correct. That is one way to do it. I could write this as a permutation. I have 20 possible people to select for president, vice president, secretary. I permute. Well, how many of them can actually win? Well, there's 3 offices, right? So 3 of them. So that's going to be 20 factorial over 20 minus 3 factorial. And from yesterday when we practiced simplifying factorials, we said, well, we count down this 20, right? 20, 19,
17.
18. We take it down to the 17 factorial. Because down here, 20 minus 3 is 17 factorial. Those will cancel, and that gives me the same answer. So that's an alternate way to do that. Let's do one more example that involves a permutation. Okay? Emma has 15 books. She's putting in order. So does order matter? Yes, because she's putting them in order on a bookshelf. That fits for books. So not all the books will make it on the bookshelf, but she's putting them in some sort of order on her bookshelf. Keyword, order. So order is going to be important because she's putting them in order. So this is a permutation. So maybe she's doing like an alphabetical order or something like that. So she has 15 possible books, right? This is the books that she has. And 4 of them are predestined. So, P for predestined. So 4 of them get to go on the bookshelf. So this is the number on the shelf. Now, we're saying order matters here because she's putting them in some sort of order. So that's going to be 15 factorial over 15 minus 4 factorial, which is 15 times 14 times 13 times 12 times 11 factorial, all over. That's going to be 11 factorial. The 11 factorials cancel. And what is the answer? What do I get here?
32,760.
32,000 what?
760.
760. So that's the number of ways she could put 4 of her 15 books in order on a shelf. Now, one more permutation. Now, this example, some worksheets, books disagree with what my argument on this. I think that's because they don't understand baseball. So let's say I have 12 team members, and I select a batting order. I'm going to then select how many of them? 9, right? So because there's going to be 9 people that I can choose on this team to put in a batting.
That's exactly how our team is.
Okay, so now many textbooks argue that this is not a permutation because either you're batting or you're not batting. I argue the batting order matters because you're not going to put your best batter in the 4th or 3rd batting position because you want them to clean up whoever's on base. You want the better batters typically on 3rd. So I argue, Mr. King argues, you want that the order does matter, that you put your batting in. So I would say we do 12, permute 9 of them. Okay? Now we can do this on our calculator without this formula. It is under, let's see, so if you take out your calculator, if you press option, so it's under option, and then you slide over to, with the arrow key, to probability, which is P-R-O-B, and you press that, you will see these 3 buttons, X factorial, NPR, and NCR, and you also have random number generator. So what we would do is we would type in our calculator 12, we would press this key, that'll give us the P, and then we'll type in the 9. And it will give us a rather large number. I'm going to move on to the next slide. It's going to be 798333600.
Is that an option?
Yep.
Oh, I don't see
So
the problem.
option,
79 million.
okay, and then you have to press the arrow key over in order to get to the word prob. Okay, and it's in there. So on your quiz and when you have it on your test, I will have questions where I want you to show this. Other questions, it'll be okay that you figure out that it is this, and then you just use your calculator to get the answer. Okay, we're going to go on to what if order doesn't matter? So like I said, some textbooks, worksheets, types of things argue that the batting order problem should be a combination, which is what we're about to do, and they say that order doesn't matter. But let's do some clear ones where absolutely we're in agreement that the order doesn't matter. So we're going to take those 20 students, and we're going to say they run for representative. Of student government. So they aren't running for president, vice president, or secretary. They're running to just be a representative of the student government. In this case, order doesn't matter. So either you're on student government or you're not. Either you win or don't. You don't get a special office. So in the other case where there was president, vice president, secretary, the order mattered because you can't be both president and vice president and secretary at the same time. you have a distinct office.
That's called a
So
dictate.
here, all the offices are the same. So that means it's a combination. So we would write 20, choose, that's how we'll read this, choose.
Really?
And, well, how many? Well, 20 students run for student government. Let's say 4 are selected. So 20 choose 4. So we're going to need a formula for this. Now it's also on our calculator. It's n factorial over r factorial n minus r factorial. So you're going to want to memorize that formula. But in this case, we have this little extra piece because we're going to divide out repeats. Okay, we don't want all the extras. So what we're saying here is that a heads, tails, heads is the same thing as a tails. Oh, I'm being too loud. I apologize.
I hear you word for word through the wall. It's an interesting
Okay,
lesson.
I'm recording, so that's why I'm being loud, but I'll try to keep it. Okay, so Mr. King will be softer. We have 2 heads here and 2 heads here. You see what I'm saying? Okay, so what we're saying in the choose is that these are the same. They're the same thing, and we'd only count one of them. Okay, so how do we put this in? 20 factorial over 4 factorial. And then we subtract those. So 20 minus 6 is 16 factorial. Now I'm actually going to take that over to the other side and show you how to do that by hand. So I'm going to grab that.
Mr. Ken, where'd you get 6 from?
Oh, it should have been 16.
Oh, okay.
So 4 factorial, is this what we had there? Okay, so like before, we'll count down that 20. I'm going to count it down to what?
16.
16. Okay, and this 4, I'm actually going to count down 2 so that I can cancel. Do you see what I'm doing here?
Can't you just divide?
Just, do you see what I'm doing here?
No.
Do you see why I counted down to 16?
Yes.
So I count so I can cancel those.
Right.
Now, I said someone was about to ask, well, can't I just cancel this 4 with that 20? Because that's not 4. What is that? 4 times 3 times 2 times 1, which is why I write it out. So the 4 does cancel with the 20, but I also have a 3 and a 2. That 20 becomes a 5, and the 3 and 2 cancel with 18 and gives me a 3. So our answer here will be 5 times 19 times 3 times 17. Whatever that is.
What do you do with the 1?
Huh?
What do you do with the 1?
Well, times 1. Yeah, times 1. It's not going to make a difference.
4,845.
Yeah.
Okay? So this is our answer. Now we can put this in our calculator by writing 20, choose 4, right on our calculator using the things that I said. If you aren't in TI, I don't know where it is. Good luck. Okay. It's in one of your menus.
I got it.
Let's do another example. You can teach each other later. Let's do another example of choosing. Let's say we have 40 cars, and 5 will be put in the showroom. Okay, so either a car makes it to the showroom or it does not. So that's 40, choose 5. Do you see the difference there?
It doesn't matter which 5.
It doesn't matter the order that the 5.
It doesn't matter which one you go with.
Yeah, as in either you make it in the showroom or you do not. So this would be 40 factorial over 5 factorial, 35 factorial, which is
658,000.
I'll assume that he did that correct.
Yeah, that's what I thought.
Okay. let's change that problem just a little bit. We have 40 cars, and 5 are lined up
In order.
near the road. Now this one, the way I worded this is a little bit ambiguous in that, does that mean order matters?
Yes, me no.
Well, yeah.
And some might say, well, it's kind of like the same thing as being in the showroom room. Either you're in the front row near the road, or you're not. But I would argue,
It is.
well, the first one that a person sees driving by is the first one they notice. So you put your best car right there, the best price, the best deal, kind of thing.
What
Get
is the
someone in.
best
So
deal?
I would argue that because we're lining something up, I argue that when we're lining something up, that order does matter. So we're going to argue that order does matter. So this would be 40 permute 5, which is going to be 40 factorial over 35 factorial. Notice that we're not dividing out any repeats. Okay, so that's going to be 40 times 39 times 38 times 37 times 36.
Yeah.
I'll let you read that one.
78,960,960.
Okay. Passwords. So let's say we select a 6-character password. Out of lowercase letters. So in this case, so this is where we're going to start distinguishing things. I have 6 things, right? How many options do I have for this first?
26.
How many do I have here?
26.
And so on and so forth, right?
Now, if you said no repeats, then you do 26 times 25 times 24
Yeah.
times.
So we'll add that. No repeats.
He is calculating.
So we're going to say, you can't have your password be A. Nothing like that. So in that case, we could write this as a permutation. We could say, well, there's 26 possible letters. Permute how many of them?
6.
Which will result in 26 times 25 times 24 times 23 times 22 times 21. Okay, whatever that is, we won't worry about that. And now we're going to adjust this same problem. We're going to select an 8-character password. The first 6, or let's go the first 4 characters, are letters, no repeats, and the last 4 characters
Can repeat.
are numbers, repeats allowed. Okay, so we have this first situation right here. So let's deal with that. I have how many letters to choose from?
26.
And is this going to be a permutation or a combination? Or neither?
Combination.
Does order matter in a password?
No.
Yeah.
Yeah, order matters in a password.
Permutation. Permutation.
So we're going to permute how many of those letters?
4.
4 of them. So that takes care of this part. Times. Now, 4 characters repeats are allowed. Is this going to be a permutation, combination, or neither?
It's going to be permutation. Oh, the bottom was going to be a combination.
I don't think it
It's
was.
neither.
Um,
Why? Because I have 4 options, right? Numbers. Well, how many numbers do I have? 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Count those, you get 10. How many options do I have for the first one?
10.
And the second one?
10.
And the third one? So that's 10 to the fourth.
Yeah,
Do you see the
fourth.
difference? Whatever that multiplication comes out to is our answer. So that's going to be 26 times 25 times 24 times 23 times whatever 10 to the fourth is.
Could you do the same thing with the first step with the 4 characters, no repeats? And just do like 26 times 25 times
Yes, but I was showing you how to write it as a permutation.
That's that.
Okay, it's a really large number. So there we go.
Mhm.
3,588,000,000.
Okay. Gibbs Ice Cream offers
Chocolate.
10 toppings. You may select 3 for your dish. Okay. Let's see here. How many toppings can you, or how many ways can you select your toppings? I'm
10
actually going
times
to
10.
do this one purposefully wrong. First of all, let's see. Is this a permutation, combination, or neither?
Combination.
Combination. It is combination because the order of my toppings doesn't matter. Either I get the topping or I do not. Raise your hand if that makes sense. That is a combination. Order doesn't matter. Okay, good. So, this is wrong.
I said 10 times 10 times 10.
Okay? Now it's on the right track. Here's the key word. I may select 3 toppings. I don't have to select 3 toppings. So I could do 2 toppings. I could do 1 topping. I could do no toppings. So I have to add all those together. Okay?
I see.
So, in our calculator, we put in 10 choose 3, plus 10 choose 2, plus 10 choose 1, plus 10 choose 0. And I add those because those are each distinct events. I get 3, I get 2,
176.
get 1, and you said 176? Because when order doesn't matter, we actually get a lot less things happen. Okay?
Wait, go back. How'd you get 176 so quick?
You probably put it in,
Put it in
your
your calculator.
but I don't know if it-
What? Oh, okay, sorry. I
Yes,
will not
it is
poke the mayor.
176. Okay. What is 0 factorial?
0.
1. By definition.
face.
Why isn't it not 0?
Listen, I'm about to tell you why. Because if I do this formula, let's say I did 12 permute 12. Okay? Now, that means select from 12 things, all 12 of them. And we would expect it to be this, by the multiplication rule. Does that make sense?
Mm-hmm.
All the way down to 1. But if I put it in the formula, I would get a 0 in my denominator if it was a 0. So we just say, because math people are like, we can't do that, we'll just say, it's 1. Okay? Because this would mean have 0 things and multiply down to 0. Doesn't really make sense. just define that as one.
Got it.
Okay, let's do one more example. The Zoe Pizzeria.
There's a one.
Yeah, that's what I was about to say. That's new, but sure.
Okay, anyways, the Zoe Pizzeria offers 3 sizes of pizza and 12 toppings. And you can have up to 4 toppings. Emma orders a pizza. How many possible pizzas?
So order doesn't matter.
Wait, you said 3 sizes of
Okay,
pizza and
okay,
12.
so she has 3 sizes of pizza. So she get small, medium, large, right? And on that pizza that she selects, so first she selects her size. So how many selections for size does she have?
3.
So we're going to times 3, right? Times 3, whatever we put in here. So we have 3 types, right? So she can have up to 4 toppings. Does she have to have 4
Oh,
toppings?
no, that would be 12C4.
12, choose 4.
Yeah, and then 12 choose 3, 12 choose 2.
Yep.
12 choose 1. 12 choose 0. Might just be one of the
And
cheese
I
people.
think we can leave off the 12. No,
What,
we
12 choose-
no, we have to have the 12 choose 0 because then that's a cheese pizza, right?
Yeah.
Okay. So we do all of that. Okay? Any questions?
No, sir.
How would you put that in the top? What? No, that's not.
Okay.